Aloha and welcome to this brief screencast on the software interface to the TeamHawaii Solar Decathlon House. I'm Philip Johnson. I'm the faculty advisor for this part of the project. The students are all off busy being productive programming, so I thought I'd spend a few moments and tell you what they're doing. To start off, let me tell you a little bit about the project. We're, for the moment, calling it iHale, the software system. And what it does is it's a system to support the collection of data about house systems, to display it in a variety of ways, to analyze the data so that you could do things like apply machine learning algorithms or other kinds of automation, and then finally to support control, either manually or through something like an independent algorithm. The systems that we're looking at initially are the consumption of electricity by the house, generation of electricity through photovoltaic panels, an aquaponics system to supply oxygen and food and plants and so forth, the heating and cooling system, and the lighting system. And for the first milestone, which is where we are now in early March of 2011, the goal is just to kind of test out our architecture and see how it works. So let me show you a little bit about what that architecture is. The organizing principle for this architecture is that all of the various systems in the house are going to communicate using HTTP. Okay, the HTTP protocol, which is on top of TCP/IP. So we're assuming essentially that all these devices probably going to have a Wi-Fi connection and therefore an internet address. And on the left-hand side, you could see the various systems in the house, like the aquaponics systems, photovoltaic, and so forth. And then they'll communicate to this kind of centralized system that we're calling iHale. And that will have a web front-end user interface. It will also store historical data about the project, because we're assuming that the house systems are pretty stupid. They can return their current state. They can accept commands to change various parameters, but they're not going to have kind of much processing power at that end. And then also iHale is going to serve as a way, kind of a communication pathway for any other kinds of interfaces that we want to implement in the future. So we might want to have tablet interfaces like the Samsung Galaxy tablet, smartphones, posting to Facebook about the house. For example, we might want to have a Facebook account which is the house itself, as opposed to the team developing the house. And so iHale could post messages to the Facebook wall from the house itself about what it's doing. Also, if we want to have things like connect whole body controllers for the system, the natural way in our architecture to do that would be to have the Connect system communicate with the iHale system about the user's intent, and then the iHale system would actually issue the commands to the various systems. So that's the basic overview of our architecture. And so you can see we have, I want to kind of briefly go over these assumptions. We're assuming that for the aquaponics, HVAC, and lighting systems, that we're going to be using something like Arduino or a related kind of system. It should be able to communicate with us via HTTP, either Ethernet or Wi-Fi, although I assume we want to use Wi-Fi because we don't want wires all around. And that means all these devices are going to have an IP address, and that a given device should probably come with some already built library code for dealing with the HTTP protocol. And if it does that, then it's pretty simple for us to provide the communication mechanism, because on top of, as long as HTTP is provided, then the actual commands to get state and do various controlling actions is quite simple. For the electrical stuff like generation and consumption, we're going to be assuming that we're using the e-gauge meters, and that they have their own HTTP API protocol, and we'll simply use that. Okay? So, for example, the aquaponics system, in the current version, in current system implementation, what we're assuming is that there's actually two devices. One device that's going to return the state of the aquaponics system, the temperature, pH, and so forth, and another device that would control the system by allowing you to set the temperature or whatever. And it doesn't really matter if there's one device or two devices or three devices. We're kind of arbitrarily making this assumption right now. It can easily be changed. So you can see we can do a get on the http://arduino-1.halepilihonua.org, and that's going to return some XML with the current state of the aquaponics system. And then we could do a put command with a payload that says, set the temperature or whatever to another device, and that would actually end up changing the devices or the actual aquaponics system in whatever manner we wanted. So if you wanted to put this together, basically you'd need an Arduino board. You'd need a component that adds in the Wi-Fi connection. So there's this thing called Y-Shield that does that. You'd need whatever sensors or actuators you want. So here's an example of a temperature sensor that you could add in. And then you need this, you need to have an HTTP library on top of which we'll write our little tiny bit of custom code to understand the gets and the puts. So that's kind of how it would work together on the Arduino side. For the electrical stuff, it's much simpler because we're just going to buy one of these e-gauge meters, and it has its own protocol for HTTP, and we just issue the get commands according to the way they want it. So for each of these devices in the house, aquaponics, HVAC, lighting, photovoltaics, electrical, we have an API specification that we've defined that says how we expect communication to occur between our system, the iHale system, and these other devices. This is kind of the place where we want to negotiate with other folks involved in the system development process to make sure that we all kind of understand how we're going to do communication. This is in essence a draft because there is as of yet no firm conclusion about how the aquaponics sensing and control systems are going to be implemented. We just essentially made some guesses about a reasonable architecture, including the number of devices and the kinds of things that can be controlled. So over time, as that becomes more clear, and hopefully that will become more clear sooner rather than later, we'll modify this API, and that's kind of forms the contract between the software side of the house and the hardware side of the house. So how are we working on this? Well, we've decided to break the system down into 3 components. One component is a front end, so that's currently a web-based, browser-based user interface that allows you to see the state of various systems and control them in various ways. There's a back-end component to the system which is focused on communication, so issuing those HTTP requests to get state data or issuing other ones that control the system in various ways. Also, the back-end provides a repository which enables us to gather historical data so that you can show charts that show how electrical consumption varied over the course of a day, and if you want to implement some more sophisticated kind of automation. For example, you'd like to say, oh, well, I noticed that the lights generally go on about 7 a.m., or people come back to the house around 5 p.m., so maybe at 4:45 p.m. I'm going to automatically turn on the air conditioner to cool the house down. In order to do that, you need historical data about patterns of usage in the past. And so we've implemented this repository that enables more advanced systems that would hopefully be implemented in the future to query historical data to learn these patterns and then do cool things. Now, the final part of the project currently is a simulator because, of course, the house doesn't actually exist yet, and many of these systems haven't been implemented. So what we've done is we've built a software system that that kind of implements that API that I talked about in a previous slide and can listen on these various ports and can respond to GET requests so that we can test out our software system. So there's 3 parts to the system, but what actually ends up happening in practice is that there's only 2 applications. There's the iHale system that combines both the front end, which is the user interface part, and the back end, which is the communication and repository part. And then that system communicates via HTTP with the second application, which is the house simulator application, which is going to respond to the various communication requests in a manner that we hope is plausible. So as of Milestone 1, excuse me, what we've done is we've implemented the front end, back end, and house simulator not once but twice. So we actually divided the students into 6 groups, and we had 2 groups each implement a front end, 2 groups each implement a back end, and 2 groups each implement a house simulator. That was done mostly for pedagogical purposes. They're part of my software engineering class, and it was I think it was useful for them to have to all obey this protocol and make sure that they were actually doing it correctly. As of Milestone, definitely not all of the functionality that we want is available. The main thing we wanted to make sure for Milestone 1 is that we could actually build these 3 different components, put them together, and they do the right thing when put together. And I'm happy to report that that's actually the case, and I'll show you that in a second. Finally, all the code is developed using open source licenses. It's available online. You can go to the URL at the bottom of this screen to take a further look at it. The student developers who've been working very hard on this project include, for the front end, Chuan Hung, Kylan Hughes, Brett Ikehara. The back end has been developed by Leonardo Nguyen, David Lin, Nathan Dorman, Kevin Long, Emerson Tabukal, Chris Ramel. And the house simulator was developed by Anthony Kinsey, Michael Sierra, Tony Gaskell, Greg Burgess, and Kurt Teichman. They've worked really hard. They've done a great job so far. And I'm very impressed with what they've been able to accomplish, and I want to make sure all of you know that this was them that did this work. The repository is at Google Project Hosting. It's called Solar Decathlon Team Hawaii. You can get access to all the code there. Here's an example screenshot of the Milestone 1 system, and I'll show you that in real live form in a second. So let's now look at the demo. So as I said before, there's 2 components to this system. There's a simulator, and then there's the iHale system itself, which is composed of a front end and a back end. So what we're going to do is we're going to start off the house simulator, and I do that by running this Java-based program called iHale House Sim Kai. .jar, and then there's this step interval, which means that the simulator takes an argument saying how often do you want the state of the system to be updated. And I'm going to say that I want the state of the system internally to be updated every 10 seconds. So what that means is that if we were to query the house for its state, 2 or 3 times a second apart, it would yield the same values, but then every 10 seconds it's going to go through some computation to change the amount of energy consumed or generated and so forth. And we could change that to any value we want. We like this step interval because it makes the behavior of the simulator somewhat predictable, and so we can see that things are working correctly with the iHale system. So what I do when I invoke this is that it's going to write out a file called deviceurls.properties. Okay, and this is kind of interesting. The notion is that we want our iHale software system to, on the one hand, be able to communicate with the simulator system, but on the other hand, we want it to be able to communicate with the actual house. Okay, and we don't want to have to actually, kind of re-implement or recompile the system in order to communicate with the house versus the simulator. So the way that we solve that problem is that we have a special file in the user's home directory in a .iHale subdirectory called deviceurls.properties, and I can show you right here. This is kind of a better formatted version of what that properties file looks like, but it looks pretty much just like this. The idea is that the iHale software system is going to look at this file to determine where it should go to find out, for example, the electrical state or the state of the electrical consumption that's attached to an e-gauge meter, or the state of the photovoltaics panels, which is attached to another e-gauge meter. And this is the IP address, essentially, that's going to be used. And you can see in the case of the simulator is all running on localhost, and it's just going to use different ports to distinguish between the different kinds of devices. Okay, so right now you can see 2, 4, 6, 8, 10, 12, 14 different devices that we're assuming exist in the actual house. And this can be expanded or contracted later. It's very easy to change, but we had to make some assumptions. The good news is that by simply using a different device-URL properties file, we can make the iHale system either talk to the simulator or talk to the actual house itself. Okay. So what I'm going to say is yes, I'll overwrite it. Okay, and now you can see that the simulator is running, and what will happen is every 10 seconds it's going to write out the current values of the state of these various house systems. Okay, so that's that. We'll just wait here for maybe a couple more seconds to see if it does it. Yeah, so it just printed out some new values there. I don't know if you missed that, but photovoltaics now has a different value. Okay, so now let's bring up the actual iHale system itself, which is a combination of a front end and a back end. As I said before, there's two versions of each of these systems, so I've just picked one combination to actually show as the demo, but there's other combinations that are possible. So we'll run this, and now you can see something interesting. As the front end comes up, it's issuing get commands to the simulator system to retrieve the current state of all the house systems. That's what, see, now it's doing it again. So it does that every, I guess, 5 seconds or so. Okay, so you can see it's getting the state of lighting, getting the state of photovoltaics, and so on and so forth. Now to actually see the front end, what we can do is go to a browser and type in http://localhost:7070. Okay, and this is what the state of the interface looks like right now. Not everything is working, but you can see it's showing you the current temperature, simulated temperature of the inside of the house, which is 68 degrees. It's showing you the energy consumption and generation. We don't have much historical data here, so it's only showing a couple data points. And we can go to things like aquaponics, and we can see that it's sensing the temperature, the pH, and the oxygen, and it has various ideas about what would be good or bad values for these, and is coloring this appropriately. We can go to, I think, temperature, and we can turn on the HVAC system, and we can see that inside it's currently assessed to be 72 degrees, and we could say, oh, that's too cold, we want it to be a little warmer, so we could type in 76. Okay, and that issues a command to the simulator to say, now I want you to kind of simulatedly activate the HVAC system and start raising the temperature up to 76 degrees. Okay, so that's a brief. We have many other panels here. They're not all implemented at the current moment. That's something we're going to be doing in later milestones for this project. Okay, so that's a brief demonstration of the system. You can see we have a simulator on the back end. We have a front end system which is querying the state of the house at regular intervals and then able to display that via front end interface. So let's go back to PowerPoint and move on. Okay, so what are the next steps for this system? We're currently starting the second milestone, and we're going to be improving the user interface, making improvements to the layouts, the functionality that's supported, the levels of control and the charting and so forth. We're going to be continuing to work on the house simulator, providing kind of somewhat better simulation, although that's not a key component, but also to provide better historical data upon startup so that the charts look more realistic. And then we also want to implement in the back end more communication channels so that, for example, if you want to later implement, communication with a tablet or communication via the Connect controller, the HTTP interface will be specified and available for development. Things that we need at this point are further development on the hardware interfaces. We've made assumptions that we're using Arduino-like controllers. We've made assumptions about the kinds of state and control that those devices can support. This, we're happy to work with our assumptions as long as we need to, but the sooner that there's some clarity about the kinds of things that will be needed from these other house systems, of course, the sooner we can converge upon a simulation and an actual system that can be smoothly shifted over to work with the real house. So thanks for listening to this brief screencast. If you have questions, well, of course, the first person you want to contact is the student lead for the project, who is Kurt Teichman, and his email is here there below. And of course, if you'd also like to, you can always talk to me, Philip Johnson. My email is there as well. Thanks a lot.